Hi, we are going to discuss in this part of the lecture 9 the multiplexers. And multiplexers are defined as data selectors. And what we mean by that, um, a multiplexer, you have typically 2 to the n data lines, and you have n selection lines and a single bit output. In this case, we call this as 2 to the n by one multiplexer. Here's an example. And by the way, a common symbol for multiplexer is to be drawn as such. So we have here two inputs. We'll call this I0 and I1, and an output Y. Okay? To describe the function, and of course we have a selection line here, we'll call it S. The function of Y or the output Y is as such. If S is 0, then we will select data from I0 and send it to the output. But if S equals 1, we will send the output from I1 and send it to Y. So really what we have here, Y equals, if S is 0, then it will be equal to I0. If S is 1, then Y will equal to I1. And we can see this concept of selecting either this I0 or this I1. That's why it's called multiplexer. It multiplexes the data from 2 to the n into a single line based on a control. So this is basically here the data, and here we call them selection or control lines. And because n selection lines have 2 to n values, we can dictate which one of those will be sent to the output. Okay, so in this case, if I want to draw the internal circuit of this 2 to 1 multiplexer, it will be something like this. So you have two AND gates. In one input there is I0, in the other input you have I1, and you have S that comes in here and inverted here, and then the two outputs go to an OR gate, and that is the value of Y. So this is a 2 by 1 multiplexer. Notice that here n equals 1. We have one selection line. Well, let's have more interesting stuff. What happens if we have um, n equals 2? In other words, I want a 4, whoops, sorry, a 4 by 1 mux. And in this case, I have I0, I1, I2, and I3, okay? And the selection lines, let's say for instance, selection line S1, selection line S1, and S0. So notice here number n, number of control signals is n, and n here equals 2, and number of data here 2 to the n, which is equals 4 data. And here obviously we have an output here of y. Okay, so what's the value of output here, y? Well, y will equal to, if S1 is 0 and S2 is 0, let me just back off a little bit, pick a different color here. Okay, so here's, so let's pick a color, let's say magenta here. If S is 0, S1 is 0, and S0 is 0, meaning I have both of these lines, this is 0 and this is 0 here, then I will pick I0 and send it to the Y. Or, now if, let's say for example, S1 is 0 and S0 is 1, okay, so in other words, I have 0, 1 sitting here, so then I'll pick I1 instead and send it to Y. Okay, let's look for a third possibility. And the third possibility is if S1 is 1 and S0 is 0, okay, meaning that I have 1 here and 0 here, then I will pick I2 and send it to the output in this case. The last case here is that if, let's say for example, if S1 is 1 and S0 is 1, which means that I have here a 1 and here a 1, then I'll send I3 to the output, and that's the case right over here. If I want to draw the gate level for this multiplexer, so notice here how the selection is happening. I'm selecting this line or this line or this line or this line based on the control signal and send it to the output. So I can now draw the gate level for this thing. Okay, and then I have my OR gate. Okay, this is Y. Okay, this is an OR gate. So if I have here, I have the first thing I have here um, is S1 prime, S0 prime, and then this is S1 prime, S0, and then this is S1, S0 prime, and then S1, S0, and then let's have those I's go in their appropriate place. This is I0 gets in here, and this is I1, this is I2, and this is I3. So for instance, let's say for example, S0, S1 equals, I'm sorry, S1 and S0 equals to 1, 0. In this case, the output here will be 0, and the output here will be 0. The output here will equal I2, whatever the case for I2, and then we will send Y will equal to I2, whether I2 is 0 or 1. Okay, so this is basically the multiplexer equations. Your notes talk about 2 points here. One, you can have active high and active low multiplexers, and you can have multiplexers with enables. You can expand on those 2 points in your notes. But let me go to an important design problem where we use the multiplexer in it most of the time. So basically, a lot of times what I want is I want to implement functions, okay, using the multiplexer. Yeah. So for example, let's say for example, I have f equals y z prime plus xy plus x prime y prime z. Okay, y z prime xy plus x prime y prime z. Okay, so in these type of questions, we need to understand how many variables I have here, x, y, z. So if I have a choice of designing the multiplexer, the easiest will be is that I will pick a multiplexer where I have the number of selection lines equal 3. So here is x and y and z. They are in these selection lines, okay? These selection lines. Now, what about the data here? Well, the data here will be fed from the value from the truth table. Uh, so this is here, let's see, 0, 1, 2, 3, 4, 5, 6, 7. Oh, I guess I don't need this one. Okay, and now this is F here. And what I need to do now is to evaluate the truth table for this function, x, y, z, f. Okay, so these are, so let's see, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 0. I'm sorry, this should be 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. And the value of this function should be, um, let's evaluate this quickly, uh, 0, 1, 1, 0, 0, 0, 1, 1. Okay. Okay. So now, then I do what? Then I copy these values over the selection line. 0, 1, 1, 0, 0, 0, 1, 1. Why do we do that? Well, there's very simple reason is that when x and y and z are evaluated, these control lines these control lines will activate the proper path here of these data, and they will be activated based on the values of x and y and z. So for instance, let's suppose for example, x is 0 and y is 1 and z is 0. So this is will activate this path right here, okay, right here. So we pre-computed this and we found out that the function should be 1. So we stick a 1 so that when x is 0, y is 1, and z is 0, we will pick this one and send it off to the f. So basically we have here the value of the truth table. This is an easy way to implement function. We are implementing function using multiplexers. But notice, number of variables equal number of selection line. lines. How many number of variables I have? 3. How many selection lines? 3. Well, somebody might make this problem a little harder for us and decide to say, I want you to choose so this is an 8 by 1 mux. I want you to use 4 by 1 mux. Okay, so let's try to do the same function, okay, with 4 by 1 mux. So the same function is here. Okay, so let's see if we can. So a 4 by 1 mux is something like this. We have here the data lines 0, 1, 2, 3, 4 data lines, and 2 selections. Let's say selection 1 and selection 0. Okay, typically selection 1 has higher priority than 0, and this is F here. So we said that F equals um, YZ prime XY plus X prime Y prime Z. Now, notice the interesting thing here in this problem is that how many variables I have? Well, number of variables equal 3, X, Y, and Z. Okay, now how many selection lines in the multiplexer? Let's see, S0 and S1, 1, 2. So now this becomes a harder problem. Okay, what happened is that we sorry, we can choose to place X here and Y here, but somehow we need to hide the Z in the data lines here. Somehow the Z need to be hidden in the data lines. Now, how can we hide the Z in the data lines? Well, to do that, what we need is we go back to our truth table, okay, and we evaluate the function, much we have done before. Okay, so here we have it's 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Let's evaluate the function 0, 1, 1, 0, 0, 0, 1, 1. Okay, notice what I'm going to do here at this moment. What happened is that I'm going to split my table based on the values of X and Y. Notice here X and Y, these are zeros. This is one section of my table. Why X and Y? Because X and Y are going to the selection lines. Now here X and Y are what? 0, 1. So another section of the table. And here X and Y are what? 1 and 0. Another section of the table. And X and Y here are what? 1 and 1. Another section of the table. So I have split this table into these sections. And now I look at every section here. What is the value of the function here in terms of Z? Notice here function equals 0, Z equals 0. Function equal 1, Z equal 1. So in this subsection, F equals Z. in this other section when x equals 0 and y equals 1. In this subsection here, the function equals 1 when z is 0. The function is equals 0 when z is 1. So really, the f equals z prime. In this subsection, the function is always 0 regardless of the z. In this subsection, the function equals 1 regardless of the value z. Then what I have, I take these values and I copy them to the input of the multiplexer. When x and y are zeros, meaning these selections are zeros, I'll have to use z. When x and y 0, 1, I'll have to use z prime. When x and y are 1, 0, I'll have to use 0 as an input to the multiplexer, and here a 1 to the multiplexer. Okay. Somebody might say, whoops, sorry. Somebody might say that, should I always pick a z? No, you can pick any of those variables, in fact. As a matter of fact, you could choose x if you wanted to, and in this case, you can have um, um, 0, 1, 2, 3, and you can have, for example, here you can have y and z in the control lines. This is another solution, and you can have here 0, x prime, and 1 and x. Okay. And it will do the same implementation as above, so a different implementation. But in this time, what I'm doing, I'm using y and z as control lines as opposed to x and y. And of course, you can have control lines as x and z, and have the y being embedded in the data lines. Your notes uses another example where we really have. Oops, I'm going the opposite. Um, your notes also have another example here where we are having a function f of 4 variables, number of variables equals 4, and we have an 8 by 1 multiplexer, so the number of selection lines equal 3. So obviously I can have um, three variables in the selection line, and one variable, which is in this case d, has to be hidden in the data. Okay, so here we have a, b, c in the selection line. Notice selection lines s2 is higher in weight than selection 1 and 0. In other words, 1, 0, 0 here reads 4, equivalent to 4, not 1. So because this will be 1, 0, 0, A, B, C, and will activate this line. Okay. All right. So you can see this is higher priority. So A, B, C. Now, what we do here, we similarly construct the truth table. This is my input, this is my function, and then I divide my table based on ABC equals 0, and ABC equals 0, 0, 1, and ABC equals 0, 1, 0, and ABC equals 0, 1, 1, etc., etc. And in every subsection, I evaluate. So here in this subsection, f function equals d, d, d prime, f equals 0, like we have done in the previous example. Then I take these values and I plug them in these. So this is here d, d, and d prime, and here is 0, 0, d, and 1, 1. Okay, and this way I have implemented a 4 variable function using 3 selection line 8 to 1 multiplexer. And with this example, uh, we have concluded our lecture 9 of the digital logic class. Thank you.